In the world of high-tech engineering, some of the most advanced materials are, well, incredibly stubborn. They've been almost impossible to work with, practically unshapeable. Today, we're going to pull back the curtain on a process that's changing all of that. So let's just start with the core problem. How do you build a single, perfect part? Something totally unique from a metal that seems to fight you every step of the way? That's the huge question facing some of our most innovative industries. All right, so this isn't some abstract problem. We're talking about the real world, on the absolute cutting edge. Think aerospace, think automotive, even custom medical implants. These fields can't just order parts from a catalog. They need specialized, high-performance components, often just a handful of them, for very specific jobs. For the longest time, the only answer was what we'll call the old way. You had to create these massive, super expensive custom molds, heavy steel dies and punches. It was slow, it was costly, and for just one or two parts, forget about it. Then a much smarter idea came along, incremental sheet forming, or ISF. This was a game changer. It uses a simple, rounded tool guided by a computer to basically draw the shape into a metal sheet, bit by bit. No molds necessary. But yeah, there was a catch. A pretty big one, actually. The very materials everyone wants to use, these incredibly strong, super lightweight alloys like magnesium and aluminum, they just don't play nice at room temperature. They resist being formed. They crack under the pressure. The new way, well, it hit a wall. So what do you do when a stubborn material just won't bend to your will? You don't just push harder. You get smarter. You introduce a new element that completely changes the rules of the game: heat. And that brings us to the real star of the show today, warm incremental sheet forming. You know, the genius of this is how simple the core idea is. Instead of trying to strong-arm cold, brittle metal, warm ISF uses a heated tool. As that hot tool moves across the metal, it creates this tiny moving hot spot. And right in that spot, the metal becomes way more flexible, more ductile. The result? You can shape it into these amazing, complex forms without it ever cracking. Honestly, the best way to think about it is like giving a potter a tiny, precise blowtorch. That focused heat makes the material, in this case our tough metal alloy, suddenly become incredibly easy to work with. It allows for details and curves that were flat out impossible before. And the process itself? It's actually pretty straightforward. First, you clamp a sheet of metal into place. Step 2, you heat up that forming tool to a very specific, very controlled temperature. And then you just let the computer do its thing. The CNC machine guides that hot tool on a pre-programmed path, slowly and precisely pushing the metal into its final shape. But here's the thing, just making it hot isn't enough. This is a science of precision. To make this work every single time, researchers had to go on a hunt. They had to find the perfect recipe, that exact combination of settings to get the best possible results without any failures. Which, of course, leads to the big question, right? What is that secret formula? How hot does the tool need to be? How steep can you make the parts? How deep do you press with each pass? Finding the answers, well, that was the whole experiment. So the scientists focused on 3 key variables they could tweak. First, temperature, the big one, obviously. They tested a range from 100 all the way up to 300 degrees Celsius. Second was the wall angle, basically how aggressive and steep can the final shape be. And third, incremental depth, how much do you push the metal in each pass? The magic combination was hiding somewhere in there. And after a whole lot of careful testing and measuring, they found it. They cracked the code. They figured out the optimal formula to finally tame these tough alloys and shape them with incredible accuracy. So what's the first ingredient in the recipe? Temperature. And the magic number is a precise 300 degrees Celsius. Hot enough to make the metal cooperative, but not so hot that you mess with its strength. That's the foundation. Okay, next up, the shape itself. With that perfect temperature, they found they could push the geometry way further than before, achieving a really steep maximum wall angle of 50 degrees. That's a huge deal for creating the kind of complex parts that industries need. And the final piece of the puzzle, precision. The perfect depth for each pass turned out to be a super fine 0.1 millimeters. It's that delicate touch that ensures a smooth finish and a perfectly accurate part. It's the fine-tuning that makes the whole thing work. So, they've got the recipe, but how do we know it actually works better? Well, the ultimate test is something called geometrical accuracy. It's really simple. It's just a measure of how well the final metal part matches the original computer file. The smaller the percentage, the better the part. And this chart says it all. I mean, look at this. On the left, with the wrong settings, the error is over 5.5%. That's pretty significant. But on the right, using that perfect 300-degree recipe, the error just plummets to about 1%. That is a massive leap in precision. It's the difference between a rough draft and a finished masterpiece. Look, this is more than just a cool result from a science lab. So why does this really matter? Because it takes a promising idea and turns it into a reliable, repeatable process that's ready to be used out in the real world. This perfect recipe unlocks so much potential. We're talking about making aerospace parts that are both lighter and stronger. We're talking about creating custom-fit biomedical implants, like a plate for someone's skull that is shaped perfectly for them, or helping car companies build and test new designs faster than ever before. It's about making the impossible possible. So, the big takeaway here is pretty clear. We now have a proven, precise recipe to shape materials that were once considered unshapeable. And that opens the door for a whole new level of next-generation engineering and design. And that really leaves us with a thrilling question to think about. For years, engineers have been forced to design things based on what materials would let them do. But now that we can form these amazing materials with such precision, what new ideas, what incredible innovations will this breakthrough finally unlock? The possibilities are pretty exciting.